How many times did you lose customers because you addressed them with your marketing campaign? You sent so many freebies and promotions that actually got annoyed on the. And how many times did you actually wasted monies in freebies and promos on customers that would have bought from you anyway? The answer usually is a lot, but there is an answer to this problem, and this answer is called uplift modeling, an innovative machine learning technique that relies heavily on causal learning and causal inference, an innovative AI concept that leverages causal relationships between causes and effects, and not just simple correlations like 99% of machine learning out there. Today, we're going to discuss the ins and outs of this novel and powerful approach with Aleksander Molak, author of the book Causal Inference and Discovery in Python. Stay tuned, because if you are a marketer, this is a game-changing technology. Enjoy!
Welcome everyone to another episode of the AI and Digital Transformation podcast brought to you by GMSC Consulting. We are your hosts, Angelique and Gabriele, and today we're going to talk to Aleksander. Aleksander Molak is based right now in Israel, and he is the co-founder of Lespire Consulting. So for today, we'll be talking about an unusual machine learning or artificial intelligence concept that I think many won't be familiar of, called causal learning. So today we'll first, I think, we will be diving deep into what causal learning is and what it can do for businesses. So I'll give the floor to Gabriele to maybe have a chat with Aleksander about this.
Yes, but maybe before we delve into the machine learning part, we'd like to know a bit about you, Aleksander. Like, who is Aleksander and how did he end up founding Lespire Consulting?
Hey, hi everyone. Hi Angelique, hi Gabriele. Thank you for the invitation, first of all. I really appreciate your curiosity regarding causality, and I hope that we'll be able to decode it a little bit for the audience today. I started my career with machine learning in academia. My first project was in academia, and now there's a tool being developed based on the project that will help people diagnose children with dyslexia in the pre-diagnostic age. So very young children, which is very important because it helps children learn techniques that can improve their future lives. Then I worked with many companies, mainly large companies from Fortune 100, Fortune 500 list. And a couple of years ago, I started working with causality. My first project with causality was during a neuroscientific hackathon, where we're exploring a topic called functional connectivity in human brains and in other systems like economics and so on. But then I was not into this topic for some time. And in 2019, when I read Judea Pearl's The Book of Why, that was a moment when I really went into this. So that was a starting point for practical, applicable causality for me. And I noticed many people are interested in this topic, and many people had a difficulty understanding this topic right away, because it requires us to abandon certain habits that we learn when we learn traditional statistics or traditional machine learning. And I think that's one of the sources of the difficulty. So Lespire Consulting came partially from this idea. It also came from a series of talks that I had with business owners and business stakeholders regarding strategy, building strategy for artificial intelligence.
So how would you best explain to a business owner who does not have a machine learning background or a mathematical background, what is the difference between the mainstream machine learning and causal learning?
Mm-hmm.
And why should they consider causal learning?
Yeah, that's a great question. I think a good metaphor to think about it is thinking about maps. I see you have a map on top of your heads here, and so we might have different types of maps, right? So when you use I don't know, things like Waze, for instance, or like you use Google for navigation when you drive a car or a motorcycle or a bike or whatever it is, then the map is very simple. It contains information about the streets and just shows you like when to turn left, right, and so on and so on. And this map is very practical, and it serves a purpose, and it helps you get from point A to point B. But if you are a climber and you want to find a new hill or a new mountain to climb, and you look at a map like this, it's not necessarily something that will give you the information that you need, right? Maybe you would prefer a topographical map where you have information about altitude of different parts of the terrain. And so classical statistics and classical machine learning, these are very useful tools for prediction. In particular for prediction under a distribution that is not changing. Okay, so if you want to predict something and we assume that the world won't change too much, then statistics, then machine learning might be a very good tool for us. But sometimes we don't have any guarantees that the world will not change in a significant way. And some questions, and I would argue that this is most of the questions that we ask in science, and many questions that we ask in business are actually questions about the cause and effect relationship. So in a sense, these are questions about, if I change something, will another thing change as well? And to answer these types of questions, we cannot effectively use traditional statistics or machine learning, because these devices are not structurally prepared. These tools are not structurally relevant to answer these types of questions. So causality is like a different type of map. Both types of maps can be useful and can bring you useful and beneficial answers, but they serve different purposes.
But it's well said. And I think to rephrase it a bit, when we talk about data distribution, as you highlighted, one of the biggest advantage is that causal learning can work better even in a different setting from the one where it has been trained for. And I think this is the next step after what we already discussed several times in previous episodes, which is the detection of data drift in machine learning operations. So as we have seen multiple times, even in churn prediction with Virginie Marelli, we know that the usual workflow of machine learning model development is collecting data, verify it works, the model, deploy the model, and then deploy a system, hyperstructure made of detectors that can understand if the data that are flowing into the model are the same type of data that the model is being used, has been trained for. And if the answer is no, look, there's new data, the data has changed, the only thing that with traditional machine learning we can do is going back to the consultant and say, look, you need to retrain your model because you don't have any guarantee on its performance in this new setting. While causal learning goes a step beyond and say, yes, the data changed, But since I understood the underlying structure, I can still use the model because I have a better understanding of the problem, and so the model can adapt. And this has by itself already huge implications because it means that you have, let's say, a much more general and extended life cycle for your model. So that's already a big advantage, but I think it does come to some cost though. It's like for example, it's my understanding that it's much harder to make a causal model than a traditional machine learning model in general.
Yes, so that's a great point, Gabriele. And I must add a little bit of complexity to what you said. So there are different types of causal models, and some of those causal models will definitely have those properties that you just described, which means that they might be robust for changes in the distribution of the underlying distribution. But there are some causal models that might require a retraining as well in this scenario. So it really depends how we structure the project, what type of tools we use, and the third point, very important, which goes back to what you just mentioned, which causal information we are effectively able to retrieve, to understand from the data or from expert knowledge and so on and so on. The more information we can have about the data generating process, this is something that, as I understand, you referred to as the underlying structure. So sometimes we talk about causal structure and data generating process. These are all the names for the same thing. If we are able to get a lot of information about this process, we can build a very, very robust solution. But sometimes this might be challenging, and there's a number of challenges on different levels related to this. So you are completely right regarding these challenges.
Thank you so much for the adding to the discussion, because even though I have a background in machine learning and I took some time studying causal learning, it's still a new field. So that's why it's so nice to have an expert like you here discussing with us. And also to give a better idea of the potential of causal learning for our listeners, we agreed before the episode together to discuss one of the potential applications, which is called uplift modeling. And also because it extends quite nicely from the episode we did about churn prediction. Mm-hmm. So just to give a bit of context to whoever didn't listen to the episode, we discussed with Virginie Marelli about how to create a machine learning model that somehow can predict the churn probability, so meaning the probability that a customer will just leave your business. And now with Aleksander, we would like to discuss what can we do of that information. Like, okay, once we know that some people have some probability to churn, what do we do? And this is not a naive problem, because the big issue is that we want to make an action, which is probably give some kind of promo or some kind of offer. And we would like to know if this promo has a positive effect on positive treatment in causal terminology, or if instead has a negative outcome, meaning that the promo will annoy more the customer than doing well, and so the people will go away. And the biggest problem here, and this is where causal learning comes into the rescue, is that we don't know both outcomes. Like to train a traditional machine learning model, we would need to know what happens if we send a promo to the person, and what happens if we don't send the promo to the person. But since in this case, we cannot do both, because once you send the promo, the person already received the promo, you don't know it. And this is one of the points where causal learning offers a unique solution to this kind of problem. Could you maybe introduce us to the approach and how causal learning can solve this problem, and and then we can maybe discuss the benefits for the business owners.
Yes, so I think you touched upon two very important things. So the first one is this tension between prediction and decision making, and the second one is how to choose the optimal decision in when we are in a scenario. So starting with the first one, as you said, a traditional machine learning model or a statistical model can tell us what is the probability that a given person will churn. And this information might be valuable in a scenario where we want to, for instance, make a report and say like, hey, we expect 2% of our customers to churn next month. But this is not enough when we want to understand what we should do in order to stop customers from churning, or try to persuade them to stay with us. And for this, we need some type of a causal model. The main challenge here, as you mentioned, is what Holland called the fundamental problem of causal inference, which is that we cannot observe two outcomes under two different treatments or a larger number of treatments for the same person in the same circumstances, right? So, for instance, if Angelique has a headache today and I come with a pill, like, I don't know, like some aspirin or some painkiller and a glass of water, and then in the alternative world, I would like to just come with a glass of water because maybe Angelique was, I don't know, we were dehydrated today, right? We cannot check it. We cannot give you the pill and a glass of water and just a glass of water at the same time. So one way to deal with this challenge is to perform experiments. Another way is to use causal inference methods and to infer this kind of information from observational and interventional data. And what we can do to solve it using causal machine learning is to try to create this alternative world. So if we have a group of customers, maybe we have 1,000 customers, and some of them are churning and some of them are not churning, and we have some historical data, and perhaps we also have some experimental data recorded. Maybe we send emails to a group of customers randomly assigned at some point, and we recorded what was their response. So among those customers were people who maybe had high probability of churn, a low probability of churn, and so on and so on. We randomly send an email saying, hey, here's a discount. Here's a discount for our new product. And then we recorded how they responded, right? So we can see, hey, some customers churned anyway, some other customers stayed, and so on and so on. If we have this data, now we can do a very interesting thing. So we can classify our customers into 4 different groups. One group is often called sure things, which means that these are customers who would not churn regardless of what we do. They just love our product, or maybe they just bought the subscriptions, they forgot. It works for them, they don't want to change it. We send an email, we don't send the email, it doesn't matter to them. The second group is called lost causes. And these are customers who will churn anyway. Whatever we do, we can send an email, we can give them a discount, we can give them 6 months for free. They don't care. They just don't want to do business with us for whatever reason. Maybe they don't need the product anymore. Maybe there is something they don't like about us. They won't do business with us, regardless if we take action or not. Another set of customers is called sleeping dogs. So these customers are happy with the product and they are happy to stay with us unless we reach out to them. So if we send an email, they got angry and they say, okay, this is too much, goodbye. And I think every business has experienced this behavior. And in particular, a colleague of mine who's working in marketing, he performed an analysis, very interesting analysis about marketing to developers. And it turns out that developers might be more likely to show this type of behavior, so react negatively to a marketing content, or at least traditional marketing content, than other groups of professionals. So this group is called sleeping dogs. They get angry when we reach out to them. So we wake them up and they are, right? And finally, we have customers who will only stay with us if we reach out to them. So they basically expect that we will give them something more. Maybe they feel like, hey, I've been with this company for such a long time, I deserve some special treatment. So we have these 4 groups of customers. And now, having the data, having the information, even estimated information about this alternative world, allows us to classify each customer to one of the groups. And so now we can use something that is called affect heterogeneity, which means heterogeneous means that things are different, right? So things might be different for each individual in our data set. And now we know which scenario to expect from which individual when we take one action versus no action, or versus another type of action, because maybe we have 4 different types of emails or 4 different types of discounts, whatever. So here we are flexible, but we can make an informed decision which customers should be targeted in order to convince them to stay with us, which customers we should avoid targeting at all costs, because we might lose them actually by targeting them, otherwise they will stay with us, and which customers we should not target because it's just a loss of resources.
It sounds like very sci-fi, if you think about it. Like most of the sci-fi films and books, like The Foundation of Asimov, kind of has this kind of concept. But concept versus reality, how easy is it for a team, let's say, to implement this? Because I don't think a conventional AI engineer would be able to know how to execute or develop a causal learning project.
Mm-hmm. That's a great question. I think that actually building uplift models is one of the low-hanging causal fruits. So this is something that companies could relatively easily implement, gaining significant benefits compared to other causal methods, right? There are other causal methods that might require a lot more effort. So here we are very lucky because we have many open source packages that implement those methods for us. And some of those methods are pretty complex when it comes to the mechanics behind the scenes. But thanks to those open source implementations, we can use them, and the API abstracts all those complexity from us. I would say that the main challenge that we have is to have meaningful data for those models, collecting meaningful data for those models, which means that there are 2 ways here, 2 paths. The first one is to collect as full description of our customers as possible. So the more variables we collect, the better results we can expect, and then perform a series of experiments. So that's the additional cost that we need to pay for getting this extra benefit. The second possibility, the second path, is to just collect as much data as possible about our customers and then build a causal model to find which variables affect which other variables in our customer's description. And then we can build an observational causal inference model. But in the marketing case, this is usually very challenging because we have a risk of something that is called hidden confounding. Hidden confounding happens when we have another variable that we do not observe, so we don't have it recorded in our data set, but this variable affects our treatment and the outcome, which means it affects somehow our decision if we send an email to a person, and it affects how they react to this email. So the second path is very challenging because it's difficult to exclude this possibility of hidden confounding.
That is why, it's usually not suggested to use historical data, but you just randomly sample new data just to avoid the confounding problem, which can be daunting for causal application.
Yes.
And before moving forward, I want to focus a bit more on the advantages of this approach versus the widespread approach, which is usually based on a couple of assumptions. First one is usually we just ignore the sleeping dogs. So we assume that there are no sleeping dogs, or if there are, they're just not relevant, so much less than the people who are going to churn. And so what the regular approach would be is, okay, let's assume there are no sleeping dogs. Let's just set a threshold on the churn probability. Let's say whoever has more than, 30% probability of churn will be targeted by our promotion. So this is what it's done now. Now, the interesting fact here, I think, is that usually this approach is very ineffective, cost ineffective, because most of the people who have high probability to churn are also people who are not going to change their mind anyway. So you might have 1,000 people who want to churn, and you're going to give away, a 50% discount on whatever you're selling. And the problem is that most of the people who should receive the promo don't really care. Plus, you're targeting a lot of people who would have not churned anyway, so you're losing money because they would have bought without the discount anyway, but you send the discount.
Yes.
So it's I like to highlight the reason why causal learning in this case it's so effective, even though it's a low hanging fruit, is that the distribution of people among these classes is really imbalanced. So the people who would be convinced to not churn only by a promo are a tiny percentage usually of the people who are going to churn. And using causal learning and uplift modeling, we can really make a very effective promotion that only affects them, preventing them to churn while not wasting money on people who would have stayed with us anyway. So that's the biggest advantage that I think it's really not exploited, because it's a relatively low-hanging fruit, because as Aleksander said, there are several libraries nowadays, all pretty recent libraries, I must say, that offer these APIs. But I would still suggest to whoever is listening and has a background in machine learning to try to implement this model without the libraries, to get an understanding of what's happening under the hood. And then once you got the understanding, you can move on to use the libraries, which probably have less bug than the code you just wrote yourself, because there are a bit of hidden details that make, let's say, the understanding of this kind of solution tricky. And on this, I really want the opinion of Aleksander, because the big problem that I found when I implemented this method is, how do we evaluate how well our model is? Because, as we said, there is the fundamental problem of causal inference. So we don't know what would have happened if the model had been different. We don't have a direct measure. We don't have a test set that says, oh, you just achieved the best performance you could. So there are only kind of indirect metrics. And so I would really like to hear Aleksander's opinion on this. Like, what is the approach you would suggest to evaluate how good the model performs, and if you can make it better?
Mm-hmm. That's an excellent question, and I think it's a very interesting question for many people who are entering the field. So there's a number of methods, but before we discuss those methods, I want to give you like a broad style of thinking that is behind some of those methods, or maybe most of those evaluation methods. Okay. Yeah. So as you said, Gabriele, we don't have ground truth. So we never observe the two potential outcomes, the two alternatives, where Angelique gets a pill and she does not get a pill. I hope that's okay, Angelique, because I'm talking at you. I hope that you don't have a headache, actually.
Well, no, right now, no.
Okay, great. That's perfect. So we don't know these potential outcomes, or these alternative outcomes. And we need to get a little bit creative here. So one idea that comes from early literature on uplift modeling is to split your data set into train and test sets. So something that we would do in classic machine learning. But we must know the outcome in both cases, right? In the training set and in the test set. So we must have already, we must have the outcome recorded in both partitions. And then we train the model on the training data. We generate predictions on this test data or validation data, if you will. And then we group observations. We group observations into deciles. Okay, so given their outcomes. So we say, okay, so here are people with the highest outcome in reality, with lower outcome, and so on, and so on, and so on. And then we compute uplift, which means this causal effect within each decile. And we see if those deciles are similar to what we observe in reality. So we compute real uplift, and we compute also the predicted uplift. Okay, now because within a decile we always have a number of observations, not just one observation, a number of observations. We can compute the causal effect within this decile. And so we see to what extent the true causal effect within decile is similar to the causal effect that we predicted within the same decile. So that's one way of thinking. And all the methods, or most of the methods, have similar way of thinking. The evaluation methods that we traditionally use for uplift modeling. One of more recent developments in this area is so-called the expected outcome measure. So now we take all the models, we also partition our data into two different data sets, and we just generate predictions, and we see which model will lead to the highest outcome, right? If the outcome is, I don't know, earnings, or it's not churning, or whatever it is. So this is one of the ways that we can effectively compare different models. And in the set of different models, I also mean a lack of model, just our previous policy. And here on a margin, I think it's very important to say we should always benchmark against something. So our default policy is a very good starting point as a benchmark. because it might be that we built a very fancy model and it seems that it works, but then we compare it to our default policy and it turns out that it compared worse than our default policy. So benchmarking is very important and something that we should always remember about when evaluating uplift models and causal models.
Yeah, that sounds pretty cool. But let's say there is a business owner that comes to you and then asks, like, try to convince me to do causal learning compared to the conventional one.
In this case, for churn avoiding, let's say, after the prediction.
Yeah. Because I think they also are wary or they're mindful of the costs. Because, I mean, check and balance wise, they need to earn from this and not have more loss. So they have to make sure that this investment, for example, will lead to more, like, not negative profit in this case.
Yeah, I think that in this case...
Yeah, go on, Gabriel.
Oh, sorry, Alexander, but I think in this case, we already touched base saying before that in general, you can optimize the investment. So unless you made a mistake in how you make the model, you are kind of guaranteed to have a better performance than the
I think
traditional
this question should be essentially reversed. So the business owner should come to you and should convince you that we should stay with predictive modeling, because this is the scenario. I mean, I understand that it might sound surprising or maybe, I don't know, a little bit rude even, but in a sense, when I think about it, the scenario where we only stick to predictive modeling, this is the scenario where we'll risk bigger losses. Now, one thing that we need to balance, and this is a very important question, is to balance the cost of experimentation, right? So, so we might, it depends on our scenario, but sometimes experimentation might be difficult. And now here you can come with a set of tools to optimize how to run experiments in order to maximize the information gain from the experiment. This is called optimal experiment theory. But there are many tools, very fascinating, like causal data fusion, where we can run an experiment that is relatively simple and then combine this with observational data that is larger and maximize the efficiency of information that we gain from this. So there are many tools that can help us with this. This is a little bit more advanced, but we can do it. So if an organization is committed to really cutting the losses and maximizing gains, and they know that they want to do it in the long term, and they look strategically into the future, this is something really worth considering and thinking deeply about this and thinking about the opportunity cost of not doing this.
Yeah, I think you should have the floor now, because we kind of discussed the ins and outs of uplift modeling, and I think we touched base with all the important key points, but the question is, how understanding is what we just said? Is there any part that is not clear? Like, what is not sounding completely understood to you as an avatar of our listener?
Oh, that's a very tough question, because I mean, we touched base on all the principles of causal learning. And I think I've just raised some red flags that a business owner would ask. And, well, now that we've talked about churn prediction, I think other applications that come to mind for causal learning could be like policy making, could be, I don't know, like what other applications are there aside from churn prediction for causal learning, so that we could cover the different sectors that these businesses could...
For uplift modeling.
Yes.
Yeah, that's a great question. So you can think about any situation or any area where you need to make a decision as a potential area for applying causal inference. Because predictive models, they don't tell us which decision is optimal, right? If you use reinforcement learning, that's another story, right? Reinforcement learning can help you make optimal decisions and so on. It can also be susceptible to confounding. It depends on the type of reinforcement learning you use and so on and so on. But this is a more advanced topic. But the basic thing is, if you want to make good decisions without modeling the alternative outcome, you are using a roadmap to find a good hill to climb, but this information is not there. So predictive modeling just doesn't bring this information to the table, right? So it all depends on the question we want to ask and the question we want to answer. If this is a question about finding an optimal policy or optimal decision, there is a place for causal modeling, uplift modeling, or other type of modeling that allows us to simulate this alternative type of reality.
And what do you think should businesses do to prepare? Like, for example, if they have to encounter with Lespire Consulting, because I don't think there are that many experts on causal learning. Like, what do they need to prepare? What kind of information should they give? Like, for example, what kind of data, for example, because the quality of the data, as you said, is very important. And maybe it's kind of different compared to the traditional mindset of what a data should be for churn prediction, for example.
Mm-hmm. I think this is a very important question. Just recently, a couple of weeks ago, I was finishing my book. So in the final chapter, I'm writing about how to collect and how to store causal data. And just last week, I read a great blog post by Emily Riederer, and she wrote about, she basically drafted a whole idea how a data storage, a data management system in a causally aware organization could look like. So data quality is always important. And as you probably experienced this, collecting data and cleaning this data is often something that takes the majority of the time of a project. And when we talk about a causally aware organization that wants to think strategically in the long term, data collection and management and metadata management is also very important. Because if we do not do this, we do not collect metadata, we do not understand the context where the data was collected, we might be throwing away information that can be very, very beneficial in the future for causal models. Because in causal models, when we build the causal structure, the model of the data generating process, this is something that goes beyond the data itself, beyond descriptive statistics in the data, right? There's a whole field called causal discovery and another broader field called causal structural learning. Both those fields are aiming at recovering causal structure from the data, observational or interventional or a mix. And this is possible to an extent, but we always need some additional assumptions to retrieve this. So in this sense, storing the data and also storing information about the context where this data was collected and maybe the methodology, how it was collected, might be very, very important.
Yeah, so based from your experience with these clients in the past, do you also need to educate, like, for example, the data science teams, because that means that they have to rethink the way they deal with the data itself?
Yeah, definitely. I think this is one of the challenges, and this is a part of my personal mission to make causality more accessible to a larger amount of people. In today's curricula in most universities, we just teach people statistics and we say correlation is not causation, which is true in most cases, not always. Depends on how you understand correlation and a number of different factors. But for whatever reason, we do not teach people how to think causally. So that's the first thing. And data management is another layer. I think when you said about re-education, maybe I don't know if it's re-education. It's just education maybe. This is something that I see all across the board. I also have the educational company Lespire.io, where I go and work with companies, mostly large companies, and I see how this needs to understand causality, causal thinking are increasing all over the market.
Yeah, definitely a need for a lot of education because it's a really underrated topic. And I mean, I can tell firsthand because I am definitely an information seeker. So, and yet I discovered causal learning and causal discovery like pretty recently, and actually thanks to you, Aleksander. So, and I realized the importance of the topic, especially from an understanding, let's say, mindset point of view, because it really, even if someone who's a professional in machine learning doesn't know how to implement like the more advanced techniques like causal discovery, structured learning, and so on. But still, understanding the concept of colliders, of data confounders, which is like properties of a causal structure, are very important to understand whether the traditional model that they might be developing is a good fit for the problem or not. And so that's already, I think, paramount. And I want to add a bit on to the answer of Aleksander to your question, Angelique, about when should someone apply uplift modeling. And I think to summarize maybe what we said, we can say that prediction modeling, which is like traditional machine learning, is very good at predicting the current state of a system, maybe like even something that we cannot observe directly. But then the problem is, how do we know what to do after? And there are some cases where there are already techniques because the map is known. Like, for example, I don't know, I want to know, I use traditional machine learning, so predictive modeling, to predict the consumption, the demand for my products, because I have an online store, for example, and I have a warehouse. But then I don't need to use causal learning to model how do I do my purchasing, because there is operational research, right? And I can use that. Or I use, again, predictive machine learning to predictive modeling to predict the status of a structure, and then I use finite elements modeling to predict whether there's a risk to the security of the building given the structure that I predicted. But there are a lot of cases where we don't have an analytical model to describe the relation between cause and effect. Like medicine, like the headache example is a very good example, because the system is too complex and there's no model, there's no digital twin, as we call it today, that allows us to make an inference. Mm-hmm. Or whenever the human basically is involved in the decision, we don't have a model. And that's marketing, sales. It's again, like we don't have any model. So actually, in all these scenarios, causal modeling, and in this case, uplift modeling, is kind of the only solution that we can resort to if we want to kind of try and make an informed decision. I don't know. Do you agree, Aleksander, on this?
Yes, I agree with this. I think it's also very interesting what you mentioned about digital twins. So I think in certain scenarios, we might have a very deep knowledge about the data generative process to an extent that we can essentially build a simulator, right? And simulator is a causal model itself of a sort, right? And this in the intersection of simulations and also using simulations for producing training data for causal models, where we can, because in a simulated world, we can generate both alternatives, right? If we have a good simulator, we can do it. this is a very interesting field, and it's a very active field of research as well.
So anything that's complex, like a complex system. Yeah.
So, do we wrap it up? Angelique?
Yeah,
I think
we can wrap it up.
This episode was really, really interesting.
Yeah, I think we'll have a thorough. I think we'll try to explain this thoroughly in social media, of course. So if people don't know, you could follow us in LinkedIn and in Twitter, where we try to explain simply complex machine learning or AI terms as well. And for sure, we'll be talking more about causal learning in the coming weeks once you listen to this. And anyway, the last question we'd like to ask.
On that, I would like to add on that and reminding our listeners that we'll add to the show notes the link to the mailing list, to the newsletter of Aleksander, where he publishes weekly updates on causal learning. It's a very technical newsletter, so it's only for machine learner engineers or data professionals in general. And also, Aleksander just completed his book on causal learning, which is called, can you remind me the name?
It's called Causal Inference and Discovery in Python.
Okay. And I don't have it yet because it was released like a week ago, but definitely on my...
It's less than a week.
Less than a week. So it's like... we couldn't have it for the episode, but...
Yeah, so we'll put everything in the show notes. So if you want to dig more or learn more about causal learning and Aleksander's work, you can check out everything in the show notes. And as I said, like the last question we'd like to ask is, aside from your book, what is another book that you would recommend for our listeners?
In the context of causality?
We could.
But not necessarily. It can also be about anything you like.
Yeah. Sorry. So I think I will stay with causality. I think this topic is important and very interesting. If somebody is just starting with causality, I think definitely they should start with The Book of Why by Judea Pearl. It's a great introductory book. And although it has some technical language inside, a little bit about statistics and graphs and so on, but it's just a little bit. It's just like a spice on the top. It's a very accessible book, and I think it can show anyone who's interested in the topic what is the value of causal thinking and causal inference, and using these particular structures that Pearl suggests, graphical structures to reason causally. So that's a great book also for people who are not technical and who are in business and people who are in science. There are many great examples from the history of science that Pearl discusses, and I just wholeheartedly recommend it to anyone.
That's a great suggestion. And Judea Pearl is one of the founder of causal learning. So it's like the Einstein of the field. So, so that's a great suggestion. And okay, so thank you again for having been our guest. And I really love the episode. And even though we went a bit more technical than usual, I think it's overall a very good show to listen for whoever is interested in understanding the world of causal learning. So thank you again for having been our guest. And
so again, if you have any questions for Aleksander and for us, and if you want to learn more about causal learning, just write to any one of us. And of course, hit the subscribe button and also like our podcast and rate it if you like to, support us as well. And that's it. And I hope everyone has a wonderful day.
Bye.
Bye, everyone.
Thank you. Bye-bye.